be treating electrostatics and hydrostatics. So it will be as fast as possible, and we'll try to hit the nail on the head. And at the same time, I would like everyone to have their writing materials, because during the course of this lesson, I'll be giving questions, and at the end of this lesson, I'll be giving questions which I'll be examining everyone so far. So this is the 8th week, and I think we've gone halfway for this night class. We have 8 more weeks to you guys exam, and I think we've gone halfway by the grace of God. So let's see how much we
Sir,
can be able to
please
achieve
make your
today.
voice to be audible now. Please.
Can other people hear me clearly? I don't know, because I think I'm speaking at the top of my voice.
I can hear you clearly. It seems
You can
like
hear me
it's
clearly?
network.
Oh, okay.
Yeah.
Okay, probably network on our end. I don't know, because I'm speaking at the top of my voice. So let's head into the lesson. So for today's lesson, the lesson objectives will be trying to see how much we can be able to explain Hooke's law, and would also be able to distinguish between stress, strain, and Young modulus, or in other words, tensile stress, tensile strain, and also Young's modulus. So also we'll try to see whether we can be able to understand and calculate pressures in fluids, and also we'll talk about Archimedes' principle and the law of flotation. And I think at the end of the lesson, we'll be able to, God willing, we should be able to get to the end of the lesson early, and we'll be able to put some practice questions that I have for you guys. So I think
Your screen, sir. Your screen, sir. I can't see your screen.
Can you see it now?
No.
I think your network is bad. I don't know, maybe you could switch network if you have double SIMs. Try switching network to see if it's going well, because I think everything is clear from my end. So let's head into the lesson.
I can see it now.
Okay, let's head into the lesson. So I said this lesson on what they call it, expansivity. And from what we have
Hello,
here,
sir. Is this the starting point? Hooke's law. Hooke's law. Is it the starting point?
Yes, this is the beginning. We are treating elasticity and hydrostatics. So for the sake of this lesson, I would like you guys to do me a favor, except in cases where you don't really hear what I'm saying, or probably my voice went out. I would like us to just be patient through the lesson, and I will try to explain. Then during the same course, I will try to make out time for this. Try to make out time for questions, so that we'll be able to cover up enough ground. So I would make out time for the question during the course of this study, and I'll see how far we can be able to achieve. So let's head into the lesson for today. So as I said, we'll be treating Hooke's law. And the law states that the extension of a spring is directly proportional to the force applied, provided the elastic limit is not exceeded. So this is one law that I think is very interesting to memorize. It says the extension of a spring is directly proportional to the force applied, provided the elastic limit is not exceeded. So that's meaning the extension of as a force being applied to a string or a spring, as a force being applied to that spring increases, so does the extension of that spring increase. So it's given by this formula: F is equal to kx. So usually it is seen as F directly proportional to x, where x is representing the extension of the spring. So what this law is trying to say is that if you pull a spring with a particular force, that spring would extend in a ratio that is going to be proportional. It will extend proportionally to the applied force. That is, if the applied force keeps increasing, the spring would also keep, the extension will keep on increasing. So this formula is important that we should just memorize. And I think for Hooke's law, it's just the basics, is the starting point for Hooke's law. So that the force is directly proportional to the extension, provided the elastic limit is not exceeded. So let's move on to the next class, to the next slide. So this is an example. This is an example trying to see how the Hooke's law is being applied. So the example says that a force of 10 newtons stretches a spring of 0.05 meter. What is the spring constant? So that's what the law is asking. It's asking that a force of 10 newton stretches a spring of 0.5 meter. What is the spring constant? So what they're asking us for is the value of K, because from this formula, we have that F is equal to Kx, where K, we have it here as the spring constant. F is the force in Newton, and extension is X is the extension in meter. So now the formula is straightforward. So as I said in one of my classes, I think 2 classes ago, I said the simplest, one very simple subject or simple subject in science is physics. But the reason why it seems a bit difficult sometimes is just being able to memorize the formula and be able to know which formula to be applied per question. Sometimes you might be needing to combine 2 or more formulas, but it's just as simple as that. Once you can be able to memorize the formulas in physics, and also after memorizing these formulas, have the ability to find where they are being applied. And once you've been able to decode where they are being applied, next thing is knowing how to combine 2 or more formulas as the case may be, depending on the requirements from the question. So now this question is just straightforward. We are given the force, we are given the extension, and we are asked to find the spring constant. So for this one, we just make K the subject of formula. As you can see here, we make K the subject of formula, put it in the formula, put the values that we're given into the formula, and we'll get our spring constant to be 200 newtons per meter. So it's that simple. It's that simple. Just know the formula that force is directly proportional to extension, and the formula is given by F being equal to Kx, where your F is your applied force, K is your spring constant, and X is the extension. So that's for Hooke's law. This is how Hooke's law question come around. Sometimes they might combine Hooke's law with some other formulas. So that's why I said it's important to know the formula per topic and be able to know when it is being combined with another formula. So that maybe you might need a first formula to get maybe the force, and from the force you can then get the spring constant or whatever you're asked to look for. So the main thing is know the formulas, know when they are being applied, and know how to maneuver these formulas. And I think you'll be able to smash your physics case. So let's go into the next portion. So in this next slide, we are talking about tensile stress, tensile strain, and Young's modulus, or in other words, it's being called stress, strain, and Young's modulus. So these parameters, they are kind of interrelated, and they are all talking about things that are springs. They are mostly talking about springs or things that are under tension. So for this
Sir,
formula, the stress, yeah, I can hear you. I can hear you. Can someone call my name? Hello, can you guys hear me?
Yes, I can hear you.
Okay, I think someone called me and I thought the person was trying to say something. So let's see what the formulas are. We have stress represented with the symbol sigma being equal to the force over area, the force over the area. So when you see the formula and you're asked to look for the stress, sometimes they might give you, this is what I meant by saying they might give you an equation or a question that probably might need you to involve another formula relating to this same topic. So now they might tell you to find the spring constant, or they will give you stress, they will give you the area of the spring. Then you then find the force using this stress formula. Then once you've gotten the force, you can now apply it in the spring, the Hooke's law expression. So sometimes you might need to combine some of these laws together or these formulas together to be able to get your final answer. But aside that, physics is very, very simple. This is very simple aside this part of the whole stuff. So the formula for stress is force over area, similar to the formula for pressure. Force over area. While the formula for strain is given with the Greek letter epsilon, and is equal to delta L, that's the extension, over L. Delta L is the extension, while L is the original length. Delta L is the extension, while L is the original length. In some textbooks, you might see it as strain is equal to E over L. Sometimes you see it as that, where they say that the E is representing the extension, or they might even say X over L in some textbooks, trying to refer to it as the extension. So the main thing is to be able to know what the letters are representing and what the formulas are saying. So for stress, stress is force over area. For strain, strain is extension over length. Strain is extension over length. Strain is extension over length. So for strain, it does not have a unit. It does not have a unit. It is usually a unitless parameter. Then when you combine stress and strain together, you'll be able to get the Young's modulus. So Young's modulus, they might ask you to define Young's modulus. So you can define Young's modulus as the ratio between the tensile stress to the tensile strain. It is the ratio between the tensile stress to the tensile strain. So, and it is given as sigma over epsilon. That's this expression we can see here. Sigma over epsilon. So this is the expression, or you can combine this portion. So you can combine this portion and this portion together, just knowing that stress over strain is equal to Young's modulus. Stress over strain is equal to Young's modulus. So the question might be as simple as asking you to find the tensile stress, and they will give you the extension, they will give you the length, and they just tell you find the tensile stress or the tensile strain. And you might be wondering, well, how do I get this? Well, it's just something that's as simple as that. Something as simple as this. So sometimes the difficult, as I think I'll be emphasizing on it over and over again because it's important that I emphasize on it. Learn the formulas, memorize the formulas. Don't just cram it. Memorize it so that you can be able to tell formulas. And the more you get familiarized with this formula, you can be able to bring off these formulas and know when to apply one to get another. So let me see. We have our example. This is our second example under this same topic. So they said a wire of length 2 meter and area of 2 times 10 to the power of minus 6 meters square stretches by 2 millimeter under 100 Newton. Under 100 Newton. So this question is very tricky. And I think it's one of the most, like, so far since my examples, I think it's just one of the most tricky examples I've tried setting now. And what this formula is trying to, what this example is trying to point out is how they can twist the question. They could possibly bend your mind. Something that is probably just straightforward, you might omit it, or think that maybe it's very difficult, while it's just something that is just staring at you at the face. So this question they gave us that the wire length, so you know that they gave us length of the wire, and area, they gave us area of the wire, stretches by 2 millimeters. So this is the extension, it stretches by this with the force of this. So now, mostly some people will just rush into this formula and say, okay, they're asking us to look for what? They say we should look for the Young's modulus. The Young's modulus Y. So some people will just rush and say, okay, they gave us from the formula is saying FL over A times delta L. So they gave us F, they gave us L, they gave us A, they gave us delta L. So that means we can solve everything straight up. So just putting out the formulas straight up. But now the tricky part of this is that they gave us our extension in millimeter, in mm. So you might not notice and you might quickly just rush up and solve your answer. You will see an answer that probably looks like the correct answer, but you'll be wrong in that you are supposed to convert your parameters to SI units. All your parameters should be in SI units. So this is one other thing that I think is very important for physics students to understand. When you see a question, ensure that the parameters are given in SI units. If any particular parameter is not in SI units, take it to SI units. This is like one of the best practices rather for solving physics questions. Your first thing should always be checking through the parameters or the question that they gave you. Is all the parameters rather in SI units? Once you be able to confirm that they are in SI units, you start thinking of formula that you would apply. Because if they are in SI units, then you are good to go. But if they are not in SI units, that means no matter how you can be able to remember the correct formula, you omitting to find out that, or you failing to find out that there is an error in the unit, or there is a possible error that might come up as a result of you not converting the unit, it can make you lose the mark for that question, even when you are very good at knowing what you're supposed to do. So this question is straightforward. Just your first step would be to convert this millimeter to meter. And that's what I did here. Where I said delta L, changing it from millimeter to meter, we have dividing it by 1,000 because 1,000 millimeter make 1 meter. So dividing 2 by 1,000, we'll be getting, dividing 2 by 1,000, we'll be getting 0.02 meter. So once you've done that, I think everything is then in SI units. So you can then apply it into the formula here. This is the formula. Y being equal to X F times L over A times delta L. So our F is 100. Our L is 2 meter. Our area, that's A, is this 2 times 10 raised power minus 6. In our extension, that's our delta L, is 0.023. So when you plug in all these parameters inside this formula, you'll be able to get your final answer to be 5 times 10 to the power of 10. So 5 times 10 to the power of 10 will be your Young's modulus. So I think that's for this one. I don't know if anyone has a question in regards to this before I move on to the next thing.
Surface, can you explain this again? Can you explain this example again?
Okay. From the example, we are being asked to find the Young's modulus. So I didn't really state it here clearly, but we are expected to find the Young's modulus. In normal exam case, they would ask you strictly that directly, will say find the Young's modulus. So now when you are given this kind of parameter, from this place, we can see from this slide that this is the formula for our Young's modulus. Stress over strain. Stress over strain. So, and that is giving us this divided by this, and this is what the expression will be giving us. The expression will be giving us this. So we have FL over A times delta L. So now with that, now from the question, we were given our F, that's our force, with this. We're giving our force to be this. Then our length, we're giving our length to be 2 meters from the question, straight up. Then also they gave us our area to be this here. Area as this. Then they gave us stretches by 2 millimeters. This is our extension, that's our delta L. So now, but the thing about this question is that normally you're supposed to just carry everything and plug into this formula directly. But now you need to know that this expression, this 2, the extension is not given to you in SI units. So you need to first, once you are given any question, I think I should talk more about this stuff more often. Once you're given any physics question, physics, they do this stuff a lot in physics, Another place that maybe is being done in chemistry, or in physics, they do it a lot, where they will give you question and the error will just be to find, to switch the units, or to convert it to SI units. So now the first thing, once you are given a physics question, first confirm that all the units are in SI units. Once you can be able to confirm that all the units are in SI units, the next thing you can then do now, you can start racking your brain for which formula would go in for the question. So now, looking at this now, this is in SI units, meter. This is in SI units also, meter. This is not in SI units, it's in millimeter. This is in SI unit, Newton. So this is the only one that is not in SI units. So we need to convert this from the unit it is in to SI units. Let's convert this to be dividing this by 1,000, dividing 2 by 1,000, because 1,000 millimeter makes 1 meter. So doing that conversion, we'll be having this as our delta L. Our delta L will be 0.002 meters. once we've gotten that, we can now plug it into this formula, plug all the parameters we're given into this formula. We're given our F, we plug in our F. We're given our L, we plug in our L. We're given our A, do the same. L, delta L rather, do the same. We've gotten our delta L to be this. So we do the same. So we're having this expression here, 100 times X, 100 times 2, all over 2 times 10 to the power of minus 6 times 0.002. So once you solve this, you should be getting your final answer to be 5 times 10 to the power of 10 Newton per meter square. Newton per meter square. So that's for this example. I think I can move on to the next slide.
Yes, sir. Yes, sir. Thank you, sir.
Okay, good. You're welcome. So now let's head into our next slide. In our next slide, we're talking about pressures in fluid. So we've talked about elasticity in spring. That's what Young's modulus and their likes talking about in spring. So now we're talking about pressures in fluids. So pressure, the general formula for pressure, we know it to be, or we're supposed to know it to be force over area. General formula for pressure is force over area. So pressure, there's a formula that gives pressure at a particular depth. There's a formula that can be used to get pressure at a particular depth. And that formula is given as this: pressure being equal to the density times gravity times the height, that is depth, I mean. So the pressure at a particular depth can be gotten by using the density times gravity times the depth, that's h, the height or the depth. So these are the parameters now. These are the interpretation for the parameters. This is representing density, this is representing in acceleration due to gravity, then h is representing the depth. H is representing the depth. So this formula for pressure can also be used as this. This is the same P, the same
So
pressure
I'm
that
not
is this.
enjoying this lecture. I'm not hearing you at all. I'm just doing only screenshot without getting your explanation.
Can everybody hear me aside her that is having this issue?
No, I can't hear you.
I can hear
I'm
you.
hearing you. I can hear you, sir.
Because I know I'm speaking, and I think I'm speaking clearly.
To
So
be audible
if you're not
before
already
now.
hearing me, I'm being audible. I'm being audible because I think other persons can hear me. I'm being audible. I'm trying to even raise my voice right now because I don't know. You told me at the beginning of the
Can you
class you're not
increase
already
the
hearing me, and
volume
I've been
of
trying.
your this thing now? I've done my own part. I've increased the volume. I've gone to settings. I increased all the volumes. I checked whether they're in order, Yet I'm not hearing you. I'm just doing only screenshot without getting the explanations.
You have an earphone because I don't know. I'm speaking. I don't know.
No,
Other
sir, I
persons can
don't
hear me.
have.
Can you guys hear me clearly? Can every other person hear me clearly? Because if it's just you, then I don't know what to
Yes,
do.
I can hear
It's not
you.
going to be from my end. If other persons can hear me clearly,
No, I can hear you very clearly. Maybe she should rejoin
clearly,
the
I
right?
can
call. Maybe she should rejoin the call. I think it's an
distance is
exhaust.
Because
full.
I know I'm speaking at the top of my voice, and I'm not speaking. I'm not talking low. So I don't know. I don't know what else I can do because I'm speaking at the top of my voice, and I don't know. Can't help that now. I don't know what to do again. It's in regards that since it's just your end that is happening, that you're the only person that is not hearing me clearly. Probably there is either network issue on your end, or maybe you should just end the call and rejoin the call. I think that would be better. Maybe you could try it that way, or maybe I cannot tell exactly what the reason. I
Okay,
don't know. There's nothing I
give
can
me
do for my
just
own
two
end.
minutes. Let me end it and rejoin, please.
About pressures in fluids. So pressure is given by the formula force over area. Given by the formula force over area, and it also can be given as density times acceleration due to gravity times the height. So that's what we can see here. This is the expression for pressure that is given as density times acceleration due to gravity times height or depth. So the pressure, general formula for the pressure that we know is force over area, and that's this. So there's another way when you try to get pressure when you're talking about fluid depth, where you need to use this formula. So these are formulas that we should write down in our notes and see when they will be useful in different question cases. So let's go on to our next slide. For this example now, we are asked to calculate the pressure at a depth of 5 meters in water. So normally, without you knowing this formula, you might be like, what am I supposed to do? Or if this is the only formula you knew about pressure, you might be wondering, they did not give us force. You might think that maybe the one that they gave you is area. You will now be wondering, what will you do? But this is another formula. I think maybe most of the time people might not really remember most of the times, but for memory's sake, just try to remember this formula, because questions can come out that tricky form where you might need this formula as this one came out. It's a simple question. Calculate the pressure at 5 meters in depth for water. So now, when you hear that they're talking about water, water has a standard density. It has a standard density of 1,000 kilogram meter cube, a kilogram per meter cube. That's a standard density of 1,000 kilogram per meter cube. That's the standard density of water. So, and we know our acceleration due to gravity to be 10 times 10 meters per second squared, or 9.8 meters per second squared. So with all this now, we already can know what the formula would be, or what we'll be using. We'll be using the formula that states P is equal to density times gravity times height or depth. So plugging every parameter into this expression, we'll be getting this as our final answer, 49,000 Pascal. 49,000 Pascal will be our final answer for the pressure. And it can be given as in terms of kilopascals, where you divide it by 1,000, that's 49 kilopascals. So that's how questions come out in this. I think towards the ending of this entire night class, I think maybe we might do something like a revision where you guys might be bringing in questions and answers, or questions, and we'll be trying to see whether we can solve them live. I'm not certain yet, but that would be a possibility that might work out. So let's see how what the next slide has. So for this question, the main thing is memorize the formula. Memorize the formula. Once you've known the formula, I think the rest is simple. So now, before I move on, I think I will need to state something about pressures in liquids, especially liquids in container. When you have a liquid in a container, something like this, maybe in a long container or a deep container, if the pressure at the top of the liquid is always less compared to the pressure at the bottom of the liquid. So this is something that you just take note of. I did not write it here, but it's something that you should use worthy of taking note of. So in a liquid container, the pressure at the top of the liquid is always less than the pressure at the bottom. So mean as you go down, as you go deeper into a liquid or into a fluid, the pressure as you go deeper increases. So it's a relationship that pressure increases with depth. As depth increases, so does pressure increase. So that's something I think you should take note of. As you go deeper, that's the same thing that happens when you try to swim. You go down underwater. It seems like as if the pressure there, things are tighter. The breathing is going to be somehow like as if they are pressing your chest. For those people that are going to try to swim, so pressure at the bottom of a liquid is always more. Pressure at the bottom of the liquid is always more. So that being said, I can move on to the next slide, which is talking about Archimedes' principle. Archimedes' principle. So this principle is also known as the principle of flotation. Also known as the principle of flotation. So this principle is trying to talk about what happens when a body is being immersed into a fluid. So from the principle, we say that a body that is being immersed in a fluid experiences an upthrust, which is equal to the weight of the fluid. So a body that is being placed in a liquid or a fluid experiences an upward force. That's what upthrust means. An upward force, which is equal to the weight of the fluid. So it is equal to the weight of the fluid. So this Archimedes principle is responsible for flotation, meaning if the weight of the fluid is heavier than you, if the fluid has more weight than you, the fluid can be able to make you float. No matter if, so long as the fluid's weight is more than you, you can float on the fluid. But if your weight is heavier than the fluid, you would displace the fluid. The fluid would have to go above you and go down. So That is what this principle is trying to explain. That a body that is being immersed in a fluid would always experience an upthrust, and this upthrust is always equal to that. This upthrust is an upward force that is always equal to the weight of the fluid, not the weight of the person, but the weight of the fluid. So the expression for this is given as buoyant force being equal to the density of the fluid times the volume displaced by the object times gravity. So this volume displaced by the object is, when you place, probably you carry something heavy and put it inside a cup of water. Maybe you carry something like maybe a magnet and drop inside a glass cup of water. The former volume of the water would increase. The previous volume before this thing was placed inside the glass would be lower. But when the object is placed inside, the object will displace some of the liquid to some extent and cause a new volume to be shown in that liquid. So this is the volume they're talking about. And now there's a force that they call buoyant force, which is relating to upthrust. It is equal to the density times the volume times gravity. Density times volume times gravity. So the weight, when you put an object inside water, the object has a weight that is acting downwards into the liquid. So what would make this object float is when the upward force is able to overshadow the downward force. So when it is more than that, it can be able to cause this object that is falling into the water to move upwards. It's going to cause the water object to be able to move upwards. So that force is known as upthrust. And this is how questions under this topic comes out to be. They will give you an expression and will tell you a block that weighs 200 Newton in air and 15 Newton in water. Calculate its upthrust. Calculate the upthrust of the water. So for this expression now, for this formula, the weight of the object is equal to this, and the weight of the object in air is equal to 20 Newton, while the weight of the object inside water is 15 Newton. So this question is not really asking us to use this formula. They're trying to find the weight of the water. They're trying to find the weight of the water or the upward force by the water. So now, if the object seems to have a weight of 20 when it is outside water, and when you now place it on top of water, the weight now seems to change to become 15. It means that the object, water has already displaced part of its weight. The weight of water has reduced part of the weight of the object. And we can tell that that weight of water is given by the subtraction of the air's weight from the fluid's weight. So that way you can be able to get the upthrust of that liquid. You can be able to get the force of that liquid, and that is the upward force within that liquid, whether it's the liquid is water or oil or whatsoever. So we can get this is one of the practical ways that they can use to determine the upthrust of any liquid. They will take the liquid, and they will hang an object by a spring or by an object by a line. They will drop the object on the liquid, and they would see the weight of the object when it's on top of the liquid and see the weight of the object when it is outside the liquid. They would hang it probably on something like a G clamp or a measuring weights balance, where all this kind of scale, all this olden day scale, where one side would be weighted, the other side would be balanced with another. So they would place this object on water and try to see the reading of the weight by the time it's placed on water, and check the reading when it is placed just on air. So that way, when this kind of experiment is done, it can be used to determine the weight, the inherent weight of the liquid. It can be used to determine the inherent weight of the liquid. So now let's see this question. They ask us to look for the upthrust of the liquid. So the upthrust of liquid is given by this expression. This expression, weight being equal to weight in air minus the weight in fluid. Weight in air minus the weight in fluid. So the upthrust is this same as the buoyant force. So once we've got from the question, I don't think the question it was written out completely. They asked us to find the volume of water that will be displaced when the object is placed in water or in the fluid. So they are trying to carry out the experiment, and they said we have this object to weigh 20 Newton when it is on air. But when we place on top of this liquid water, it weighs 15 Newton. So now let's see how much is the strength, that is the force, the upward force, that's the upthrust of the water. That's the first question. And next, they're now asking for the volume of water that was displaced by this object. If this object was dropped inside, that will be displaced by the object if the object is dropped inside water. So to get the volume that is going to be displaced, we are going to use this formula where FB is representing the upthrust or the buoyant force, and is equal to the density of that liquid times the volume of that liquid times the acceleration due to gravity. So when you put in this formula and make your V the subject of formula, you can be able to get your upthrust, and also you can be able to get your final volume. That's the volume displaced. I don't know if anyone is confused about this.
Yes, sir. Please, can you come again, especially in that explanation you made about the upthrust?
Okay. Upthrust is
Yeah.
first, it is the force that is being exerted by a liquid on an object. The force that a liquid exerts on an object is called the upthrust. The force that a liquid exerts on an object is called the upthrust. So now,
Sir.
so then the next one was when we tried carrying out an example. So let me explain the Archimedes principle from the beginning. So when we hear the word Archimedes principle, this principle is talking about the principle that tries to govern flotation. It's principle that is responsible for objects to float. So the principle tries to say that when an object is being placed in a liquid or in a fluid, usually liquid, that there is something that always happens. The liquid would exert a force on that object, and that force that the liquid exerts on that object is what is called upthrust. So the force exerted on the object by the liquid is called the upthrust. So when the upthrust is greater than the weight of the liquid, or equal to the weight of the liquid, or equal to the weight of the object, sorry. When the weight of the liquid, that is the upthrust, when the upthrust is equal to the weight of the object that is being placed in the liquid would most likely float. So what am I saying? It's just like trying to say that, okay, we have water, and the water, they say there's a weight that water has to push objects upwards. So now you're not trying to say that before anybody will be able to float, the person has to be able to be as light, or be light enough that the liquid, the water, can be able to lift the person before the person will be able to float. So now this particular principle, there are some other principles that have been manipulated to be able to make something as big as a ship float on water. There's a lot of fluid dynamics principles that we are being observed in the case of larger size objects to make them float, and even different objects to make them float. So sometimes, basically, according to Archimedes principle, for objects to float, the upthrust needs to be greater than the weight of that liquid. According to Archimedes principle, the upthrust, that is the weight that the liquid is given on the object, must be greater than the weight of that object. That's according to Archimedes principle. So now, this is the principle that tries to govern
Is
flotation.
it
And there's
greater
a
or
formula that
equal to? Hello, sir. The
once it's
upthrust, is it greater or? Okay, equals
equal
to
to
the weight
or
of the
greater,
object. All right.
equal to or greater can lead to
All
the
right.
liquid, can lead to the object floating. So now, the simple formula for the Archimedes principle is given by this expression: buoyant force being equal to density times volume times the gravity, where the buoyant force is the thing that is representing the upthrust. So you might see in some formula that they are saying upthrust is equal to this. In some places, you will see it as buoyant force is equal to this. So buoyant force is the same thing as upthrust. Buoyant force is the same as upthrust. So they might ask you to define buoyant force. They're asking you to do the same thing to define upthrust. So these are ways that they can trick the questions to come out, to probably to deceive you guys, or to test your knowledge, not really deceive, to test your understanding of a particular concept. So buoyant force is another name for upthrust. So this is the general expression for buoyant force. General expression for buoyant force. So now when you are given question under this stuff, it's important to note that the density of water, because most of the times the question will be relating it to water. The density of water is always 1,000 kilogram per meter cube. The density of water is always 1,000 kilogram per meter cube. The density of water is always 1,000 kilogram per meter cube. So in case you are given a question and you look like as if they just gave me only one parameter, I cannot solve this thing. Sometimes they believe that you should know dense acceleration due to gravity, and you should also know the density of water. You get? So they might just give you only the volume and tell you to find the upthrust. They might give you only the volume and tell you to find the upthrust. So you might be wondering, where would I start from? You are supposed to know that G is representing acceleration due to gravity. That is 9.8 or 10. Density, so long as you're talking about water, the density of water is going to be 1,000 kilogram meters per meter cube. So that way you can be able to solve and get your final answer. Now, this is another way that the question can come out. So they said a block weight of 20 Newton in air is known to weigh 15 Newton in water. It weighs 15 Newton in water. So we are supposed to calculate the upthrust of this liquid and also calculate the volume that will be displaced by the object when the object is placed in this liquid. So the liquid in this case is water. So the first thing we need to know is there's an experiment that tries to weigh, or that you can use to theoretically or practically carry out an experiment and find the upthrust of a liquid. And that experiment is you would weigh an object in air and also weigh that same object in a liquid when it is placed in a liquid. So you completely immerse the object inside the liquid and you check the weight of that object. The weight of that object that you get is going to be lesser than the weight of the object when it is in air. So now, to get the upthrust of that liquid, the upthrust of that liquid that the object was placed inside, you then need to subtract the weight in air from the weight in the liquid, because the liquid would reduce some of the weight. So this is a practical way to determine the weight of the upthrust of a liquid. So now, with that, we can be able to use that expression, that knowledge, to get the upthrust of this liquid. We can be able to use to get the upthrust of this liquid. So upthrust is equal to weight in air minus weight in fluid. Weight in air minus weight in fluid. So 20 minus 15 will give us an upthrust of 5 Newton. So with this knowledge now, we can now say, okay, we've gotten our upthrust or our buoyant force. We can now be able to calculate the volume that will be displaced when this object is allowed to be immersed in that liquid. The volume of that liquid that will be displaced when the object is allowed to be immersed in that liquid. So just like as if you tie stone and you drop that stone inside a glass of water, the volume that you are seeing before the stone enters the water, when the stone enters the water, the volume will increase. That is, the size of the water will go up. That's what I mean by the volume is increasing. So that is, we're trying to check how the volume changed. How the volume changed as the object is dropped inside the liquid. So to get that now, you will now use this formula, this buoyant force formula, that F is equal to the density times the volume displaced times acceleration due to gravity. So we know our upthrust now, which is our buoyant force, to be 5 Newton. 5 Newton. And we know our density to be 1,000 kilogram meters per second. We know our acceleration due to gravity to be 10 or 9.8. And we can be able to make our V series of formula, and that will be having this expression. So when we have this expression now, we can then impute all our parameters and get our final answer for the volume to be this 0.0005 meter cube. So this will be our final answer for the volume. And that's the same representation here and here. These are upthrust, 5 newtons, and our volume displaced to be 5 times 10 to the power of minus 3 meter cube. So I hope it's clear now.
Sir, please, I have
Hello?
a question. Hello, sir.
Yeah, I can hear you. Yeah, I
Sir,
can
please,
hear
I
you.
have
Go
a
on.
question. Our fluid density,
Yeah, I'm listening.
is it constant?
Yes, it's constant when it is talking about water. So if they talk about oil, they'll give you the density for oil. But in case they say water, they will not give you density for water, because they expect you should know that the density of water is 1,000 every time, 1,000 kilogram per meter cube, kilogram per meter cube, kilogram per meter cube. I'm emphasizing on
Okay,
that so
sir.
you'll
Thank
be able to be aware. Yeah, you're welcome. So now let's head on to our next slide.
So I have a question. This
Yeah.
volume That volume,
Yes.
right? Please, how did we get that 5.0?
Okay, they use standard form. This is the answer. This is the volume here, 0.0005. Then changing it to
Okay.
standard form, that is moving the zero to the other side. Changing it to standard form, that is now you move the zero four times. One,
Yes.
two, three,
Oh,
four.
I understand.
Then you'll be having five. So that's how they got it there. So now we can move on to our next slide. And this is a combined problem solving. So I'm supposed to give this to you
Yes, sir.
guys to solve. Supposed to give this to you guys to solve, but let me just explain it because of just for explanation's sake. The question is saying a spring is suspended in a liquid and stretches 0.03 meters under a 6 Newton force. Find K. So this is just trying to stretch your mind to the first thing I gave to you guys, the first topic under elasticity, where I talked about force being directly proportional to the extension. So they gave you the extension here as 0.03, and then now they gave you the force to be 6 Newton. They are now asking you to check for the K, that's the spring constant. So to just get this is just to make K to just a formula, and you'll be having your final answer to be 200 Newton per meter. Newton per meter. So then now we now have said if the spring holds a body in water and the extension increases, calculate the buoyant force. If the spring holds a body in water and the extension increases, calculate the buoyant force. So let's see how we would solve this portion. They said if the spring holds a body in water and extension increases, calculate the buoyant force. So if this spring is known to hold a body inside water, in the first question they said a spring is suspended in a liquid and it stretches by this. So now if the spring then increases in its what they call it increases, it's just like as if you're trying to tell you that the extension is increasing, though they did not give us the parameter by which it increased. They're asking us to find the buoyant force. The buoyant force will be same to this our F. We can use the same formula because now we already know the spring constant. Then now we need to know the new extension. So with the new extension, we can be able to calculate the force, which will be similar to the buoyant force. So that's actually how this question it can sound different, but it's just the same thing. First, you need to just get your spring constant, because since you're talking about spring, you need to talk about the spring constant. Once you got in the spring constant, you can be able to get any other force that's acting on that spring. So knowing the extension, you can also be able to get the extension by knowing the force. So they're now asking us if the spring holds a body in water and the extension increases, it means that the force has increased. So you need to get that force that has increased. And that force will be similar to the buoyant force in this case. So I don't really observe that I did not solve this thing here. I thought I solved it in the next slide. I think I omitted this. So the formula is just the same now, but in this case now they're asking us to now find our F. Yes, they're asking us to find the F. So now they did not also give us the extension. So if we are given the new extension, if it has increased, maybe twice the normal length, it has increased, you just know your new X has a value. You already know the K. K is always a constant because it's the spring constant. Then F can change. So is that F you're not going to look for in that case? So I think that should be that for this. So summary for what we've talked about since the beginning. I don't know. Summary for what we've been talking about since the beginning of this lesson. We talked about Hooke's law. And I said for Hooke's law, we know that our force is equal to the spring constant times the extension. This is a constant formula. So if you're trying to write out the formulas that we used for today's lesson, these are the formulas you should write out. The formulas you should write out. All these formulas, and maybe you would then include that upthrust is equal to weight in air minus weight in liquid. So that's how another way to get upthrust. So with all these parameters, we can be able to say we have fully covered this topic under elasticity and fluid pressure. With all this, we can be able to say we've been able to cover elasticity and fluid pressure. So now I have questions for you guys. I have questions for you guys, and it's 10 o'clock. Can you guys hear me? Hello?
Yes, sir. Yes, sir.
Okay. Can every other person hear me too?
Yes, sir.
Okay. Okay. I was always saying that maybe it's now that your own network is clean. Some people are not hearing me now. So thank God for the clean network. So now I have practice question for you guys, and it's 5 questions. The first one we are asked to find the force, and a force we are saying that a force of 15 Newton stretches a spring by 0.05 meter. Find the spring constant. So this should be straightforward. The question 2 is saying find the pressure at 10-meter depth in a fluid of density this. So I believe already we should be able to remember the formula that can be used that can be applied to this question. The third is saying a 25 Newton object weighs 20 Newton in water. Find the upthrust and the volume. I think this is similar to what we solved not long. And now they asked us to define Young's modulus and also state its units. So I think this one, we know that Young's modulus is tensile stress over tensile strain. And we say tensile strain does not have a unit, meaning that the unit of Young's modulus is the same as the unit for tensile stress. So the unit for Young's modulus is Pascal. Young's modulus, the unit for Young's modulus is Pascal or Newton per meter square. Or I think Newton per meter square is the unit for Young's modulus. From the beginning here, I think I wrote it down here. Yes, I think I did. The Newton meter. No, this is not the question. This is here. Newton per meter square. So this is the unit for Young's modulus, the same with the unit for tensile stress. Newton per meter square. So the reason why this one is not affected is because this one does not have a unit. So meaning that the unit for this is equal to the unit for this. So I think that's for that one. Then the fifth question says a wire of area 1 times 10 to the power of minus 6 meters squared stretches 1 millimeter under 200 Newton. I would like everybody to just solve number 5 for me. I would like everybody to solve number 5 for me on this call before we end this class. But I think we have come to the end of this lesson. So I would like everybody to solve this question 5 for me. And someone should give me the answer. I will need to add one parameter to this question. After you've written this, right? Take the wire's length to be 2 meter. Take wire length to be 2 meter. Take wire's length or wire's original length to be 2 meter. So write that. Take wire's length to be 2 meter. Take wire's length to be 2 meter.
Sir, but is it inclusive in the question?
Yes, it's part of the question. It's part of the question. It's part of the question. On a normal, if you are not given the wire length, you would assume it to be 1 meter. If you are not given, if you were to be in an exam scenario, you would not say the question is wrong. If you are not given the wire length on normal circumstance, you would just assume, you write it in your solving. If it's a theory question, you say, assuming wire length to be 1 meter. But even if it's an objective, you would still also assume it to be 1 meter. And most likely you will see your answer. Or in this case, I'm giving the wire length to be 2 meter. I think we have 3 minutes for 3 minutes. I said 7 minutes for this. So we are solving question 5 first, and we have to calculate the Young's modulus. I think so, yeah, the y. So who has solved the correct answer? Who has gotten the correct answer? Okay, once it's 10-10, I would call out the correct answer, and think then we'll call it a day.
Hello, sir.
Yeah,
Hello,
I can
sir.
hear you. Yeah, I can
I
hear
got
you.
zero. I got 0.002.
0.002.
Yeah, it's on.
Okay. Okay, does anyone have another answer or a different answer from that?
So what's small though?
Hello, sir.
Yeah, yeah, I can hear you.
Sir, are we doing number by number or how are we doing it?
Am I doing it as now?
Like, are we
You
going to
said,
score the number?
So I
Are
got
we
yeah,
going to
just
score
if you have,
number one and three?
yeah, just call your final
hello.
answer. Let me hear. In case even, yeah, I can hear you.
I got 7.996 times 10 raised to power minus 04.
Okay. Who else has another answer? Who else has another answer? I'll call the correct answer, and whether you're correct or you're wrong, I really appreciate your efforts so far. And if you are still solving and you feel that maybe you have an answer, maybe your answer is different from the answer or the answers you've heard so far, just try. There's no harm in trying. There's no harm in trying. I always had this belief before. I always had this belief when I was still in school. I always had the belief that I'm very good in this thing. I'm very good in this thing, and I barely tried. I barely made attempts. And I found out that most of the times, even in stuffs I knew very well, when it comes to exam scenarios, I would just fail. And I was wondering why. So I met with someone then, and the person told me, you don't do practicals by yourself. That most of the times, the errors you should make in the exam, if you don't practice by yourself, you'll be able to find those errors. And when you are in the exam, even if you want to make those errors, you remember that you made before and you can correct yourself at that point. So from then, I was like, wow, okay. When I started practicing, and that was the first time I started seeing like serious breakthrough in that particular subject, because it's not that I did not already know it. I know everything off and I can tell things, but when it comes to writing the solvings down, because I'm the kind of person that when I read, I don't even maths, I don't read with my hands writing. I read maths with my just reading it from book. I barely practice, and I understand it, but some normal error, all these plus and minus error that someone could make, all this kind of careless error, I could not make those mistakes on my head. But when I start writing, I will make those mistakes. But as I started practicing, it became obvious that okay, there's some things that I might just carelessly omit, and those things could be giving me wrong answers sometimes. So even if you don't really know how to try it, when I paste the answer, try it for yourself and try proving me whether I'm even wrong. So even if I paste the correct answer, try checking whether I'm wrong. You get, because I've taught people the principles, I've given people the formulas, and I believe people should be able to know it for yourself. So try, even when I give you the final answer, try testing it. So after this class, I will be giving the PDF for this lesson, and I would also paste the correct answer. So that will be all for this night's lesson. That will be all for this night's lesson. I don't know. Um, I don't know. 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 You know. Okay. So I'll be saying good night to everyone, and thank you all for attending today's night class. I wish you all
But
success in your exams as
there
you
is
practice.
something in this question and answer, sir. Number two said, which
Okay. Yeah.
formula
This
would you like? Which
like
formula would you
explained
like?
again. Which formula would you like
Yes.
explained again? Archimedes principle. Okay. Archimedes principle. I think it's just there are two formulas for Archimedes. Basically, this is just a simple formula for Archimedes principle. Just this: buoyant force is equal to density times volume times gravity. 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 That's the up thrust is equal to density times volume times gravity. The buoyant force is equal to density times volume times gravity. The up thrust is equal to density times volume. So if you can get yourself very much acquainted with this formula, I think there's nothing else in Archimedes principle that you should need to
You said
memorize.
10 times. Is it pressure? That P?
This P is density.
Okay, P
Density
is
sit
the
here.
fluid
Fluid,
density. Okay.
yes, fluid density. Then the V is volume displaced. Then we have our G to be acceleration due to gravity. So that is for Archimedes principle. Up thrust now is what is the same thing as this buoyant force. So there are two ways you could see this Archimedes formula, this Archimedes principle formula. This is the basic way. This is the normal way. But now, in a case when you're trying to compare the weight of an object in air and the weight of an object in water, there will be a new formula for the up thrust or for the buoyant force. And that formula will be weight in air minus weight in water. Up thrust will be equal to weight in air minus weight in water. Up thrust will be equal to weight in air minus weight in water. So that's the formula. There are two formulas under Archimedes principle that I think you guys should memorize. First is this one, basically this one. Then next is for twist case or twist cases, where they would ask you to find the up thrust and they will be mentioning something like water, weight in water, and they'll say weight in air. So that one is very simple, just subtraction. Subtract the weight in air from the weight in water, and you have your answer. So I think that's that for that. Okay,
If
okay.
we are asked
So
to
with all
state
this
the
being said, okay, if we ask to state this principle, the principle states that when a body is immersed in a fluid, this body experiences an upthrust, and this upthrust is equal to the weight of the fluid being displaced. So this is the principle.
okay.
Archimedes' principle says that when a body is being immersed in a fluid, the body experiences an upthrust, which is equal to the weight of the fluid being displaced. So that is the principle.
Okay.
Any other question before we call it a wrap?
Yes. The elasticity, the modulus. I didn't quite
Okay, Young's
understand it.
modulus. Okay, the
Yes.
Young's modulus, it has a simple formula, just stress over strain. So if you can know what stress is and know what strain is, you definitely know what Young's modulus is, because Young's modulus is this one over this one. Stress over strain is Young's modulus. Stress over strain is Young's modulus. So when you can be able to, so the combination of these two formulas, combining these two formulas is what gives you the simple formula for Young's modulus. This. So you might be given stress as an entity in question, or as a parameter in the question, and you can be given strain as another parameter, and it will tell you to find the Young's modulus. You might be looking for force, looking for length, looking for area. Why they just gave you stress and strain? So the formula can be Young's modulus formula can be in two forms: either stress over strain, or this force times length over area times extension. Force times length over area times extension. So that's the formula for Young's modulus. And it was gotten from the combination of stress and strain, where stress is equal to force over area. The same thing with pressure, force over area. then strain is equal to extension over length. So, and strain does not have a unit. It's a unitless parameter. So you might see some, if it's someone like me that's probably setting your exam question, I might set maybe the final answer might be 2 for strain. I would say 2 Newton. I would say 2 Pascal. I would say 2 kilometer, something. Then I would say 2, ordinary 2. So that what I'm trying to test is your understanding that strain does not have a unit. So just pay attention that strain does not have a unit. Stress has a unit. And Young's modulus is the ratio between stress and strain. So that's for Young's
There's
modulus.
something you said. You said that that the strain is extension times what?
Over length, extension divided by length.
Is the stress?
Extension over length is strain,
Is the stress?
extension over length. So when strain, strain. So
Okay.
when you see delta L, this delta L represents extension. Delta L represents extension. So that's what I'm talking about. Delta L representing strain or extension, sorry. Extension over length L.
Okay. I think I have question there from what I jotted down before.
Okay, I'm hearing.
Delta, yes, delta share over delta strain. How is it the same thing as stress over strain?
Is tensile stress over tensile strain. I did not say delta. The tensile, Tensile, tensile,
P,
not delta.
please,
T
you are
for
not
T.
very well. P,
T for toy.
P,
Or T for thank God. T for thank God. And tensile, Tensile.
Okay.
Tensile.
Okay, tensile
Tensile.
stress, tensile strain.
Uh,
But you
yes,
represented
yes.
it as delta.
Okay, no, sigma, this symbol here.
Okay.
Sigma. That's stress.
SIMA.
Then yeah, sigma, SIGMA. Sigma. Then this one is representing GMA.
Okay.
Then strain.
Right.
We have this as our strain. This coily E. Our strain is represented by this E here. This E that is like this here. This is our strain.
The strain is changing length over length.
Yes, change in length over length or extension over length.
Okay, change in length is extension.
Yes.
Okay. Thank you, sir.
Yeah, welcome. So I think I'll be sending the correct answer, the solvings for the correct answer. The correct answer is 4 times 10 to the power of 11. That's the correct answer. 4 times 10 to the power of 11.
4 times
4
10
times
raised to
10 to the
power
power of
11.
11. Yes, that's the correct answer.
There is
I
no
think I'm testing it.
no minus 11.
So this is the
Just
answer.
11.
Yeah, just 11.
4 times 10 raised to power 11.
Yes. So I'm pasting it on the group now, and that's it for this lesson. I've pasted it. I think I'm also sharing the slide for today's lesson at the same time.
Can I ask you a question there?
On the group? Yeah, you can ask question on group, but
I said now that's 1 millimeter. You change it to meter.
Yes, you change it to meter. That's
0.001. meter.
Yes.
Is that not true?
That is divided by 1,000.
Yes. That should be 0.001 meter.
Yes.
Mm-hmm. When you divide this length now 0.001 meter by area, what did you get, sir?
See it up now. See, we have y is equal to f times L over a times
A.
delta L. So our
Yeah.
f is 200. L is
Mm-hmm.
2 because I said you should take your length as 2.
Mm-hmm.
L is 2. So then
Mm-hmm.
over our area is 1 times 10 to the power of minus 6 times 0.001. Times
Mm-hmm.
0.001. So if you multiply the ones up, it will give you 400. If you multiply the ones down, it will give you 1 times 10 to the power of minus 9. 1 times 10 to the power
So
of
this
minus 9. So if you then do your final answer,
the change in length, is it the stretch?
yes, yes.
Okay, that's where I failed it.
That's
I
just
failed. I went
that is
and
about solving.
is this the 2 meter you gave us now that confused us? I subtracted that 0.001 from 2 meter, and I got
Okay.
1.999.
Oh,
So
okay.
which means
Okay.
the 2 meter you
So
gave
that
us did not need to play there.
is just is it that is L that is up, F times L. It is the 2 meter that is L. The
Okay,
length.
okay, okay,
Yes. Yes.
okay. I've taken my correction. Thank you, sir.
Yeah, you're welcome. So I think we've come to the end of this lesson, and I'll be saying good night to everyone. So thank you
Thank
for
you.
your time.
Wonderful
Thank you for
lecture.
your
God
presence.
bless you.